Hello students, എല്ലാവർക്കും സുഖല്ലേ? ഇന്ന് നമ്മൾ ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻ തിയറം ആണ് ചെയ്യാൻ പോകുന്നത്. ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻ തിയറം. സോ വാട്ട് ഈസ് ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻ? ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻ എന്ന് പറഞ്ഞാൽ എല്ലാ ഫംഗ്ഷൻസും, അതായത് സപ്പോസ് y is a function of x, but y may not be able to write explicitly in terms of x. അത്തരം ഫംഗ്ഷൻസിനെയാണ് നമ്മൾ ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻസ് എന്ന് പറയുന്നത്. For example, x to the power 4 plus y square x cube plus yx plus y minus 1 equal to 0. ഇവിടെ എക്സും വൈയും തമ്മിലുള്ള ഒരു ഫങ്ഷണൽ റിലേഷൻഷിപ്പ് ഉണ്ട്. y varies with respect to x, but satisfying this equation. But here in that equation, y cannot be written as a function of x. So in that case, we say y is an implicit function of x. Now, ചില ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻസിനെ നമുക്ക് എക്സ്പ്ലിസിറ്റ് ആയിട്ട് എഴുതാൻ പറ്റും. ഉദാഹരണം, സപ്പോസ് f of x, y equal to y minus x square equal to 0. So here y can be expressed explicitly in terms of x, namely y is equal to x square. So a most general function in x and y is of this form: f of x, y is equal to 0. That expression may be an implicit function or maybe an explicit function. So the question is, under what conditions an implicit function f of x, y equal to 0 can be solved for y in terms of x? That is the question. And in implicit function theorem, we try to answer this question. Or you can tell the other way around also. X as a function of y. When you can solve for x as a function of y. So when an implicit function becomes an explicit function. So that is what the implicit function theorem says. ഞാൻ ഒരു വീഡിയോ ലിങ്ക് തന്നിരുന്നു NPTEL-ലെ. അതിൽ പ്രൊഫസർ ബാലാജി അദ്ദേഹം ഇംപ്ലിസിറ്റ് ഫംഗ്ഷൻസിനെ കുറിച്ച് ഡിസ്കസ് ചെയ്യുമ്പോൾ he took the unit circle x square plus y square is equal to 1 and look at the points 0, 1 and 0 minus 1. There, in that, at that point, let us say at the point 0, 1, you take a point on the y-axis close to this point. That means you are fixing your y. I have two values for x. Satisfying this equation, x square plus y square minus 1 is equal to 0. So here for this y there is no unique x. So now under what conditions you can make sure that for a given y there is a unique x? So that's what we are trying to solve in implicit function theorem. And first let us prove a linear version of the above problem f of x, y is equal to 0. That means suppose your f is linear, namely a of x, y is equal to 0. Can I solve y in terms of x or x in terms of y? That's what we are going to answer for the first time. And one more thing, in the general setup, this x and y may be vectors. Okay. So we will start with vectors x and y, and we want to solve for y in terms of x or x in terms of y. And we will first look at a linear version. That means your f is some a linear transformation. So we need a notation. Suppose x is equal to x1 etc. xn is a vector in Rn, and y is equal to y1 etc. ym is a vector in Rm. Then by the ordered pair x comma y, we mean the vector x1 etc. xn comma y1 etc. ym in Rn plus m. Okay. Now take a linear transformation a from Rn plus m to Rn. So this can be represented by means of an n by n plus m matrix. Okay. So this is that n by n plus m matrix. A11 etc. A1n, A1 n plus 1 etc. A1 n plus m etc. Finally an1 etc. an n plus 1 etc. an n plus m. You have a linear transformation from Rn plus m to Rn, right? So take a vector in Rn plus m. So this is that vector h1 etc. hn, k1 etc. km, and you will end up with a vector in Rn, right? Here you have n rows and n plus m columns, and here you have one row, sorry, n plus m rows and one column. So you will end up with an n by 1 matrix. That means you will end up with a vector in Rn. Okay, now I am going to split this. How do I split? So I will take this portion a11 etc. a1n etc. an1 etc. ann, and it can be applied to the vector h1 etc. hn. And look at this portion. This portion can be applied to the vector k1 etc. km. Okay. Now this portion, this submatrix, I will denote by a sub x, and this submatrix I will denote by a sub y. Instead of a sub x, I can use a1, and instead of capital A sub y, I can denote it by a2, whatever. Okay. So now this is my capital A of the ordered pair vector h comma vector k, and the final answer, when you multiply this, you will end up with a vector in Rn. And what I am going to do is take this whole of A, apply to the vector h1 etc. hn, then remaining 0 etc. 0, plus the whole matrix A into the vector 0 etc. 0 k1 etc. km. So when you multiply this and this, it will be this into this plus this into this. Okay. So this A of h comma k is split into 2. A of h comma k is split into 2. How do I do? Look at A of h comma 0, and then look at A of 0 comma k, where this 0 is the 0 vector in Rm and this 0 is the 0 vector in Rn. and this expression I am denoting by AXH, and this expression on the right side I am denoting by AYK. So every linear transformation from Rn plus m to Rn can split into two linear transformations, Ax and Ay, defined by Ax of h is equal to A of h comma 0 and Ay of k equal to A of 0 comma k for h in Rn and k in Rm. Then you can easily verify that Ax is a linear transformation from Rn to Rn and Ay is a linear transformation from Rm to Rn. And A of h comma k is A of h comma 0 plus A of 0 comma k, which is AXH plus AYK. So why did we do this? We want to solve a linear version of the implicit function theorem. So what is that linear version? Let us go to that linear version of implicit function theorem. So suppose I have a functional expression between h and k. So what is that functional equation? This thing. H and k, h varies with respect to k, or k varies with respect to h, but satisfying this equation. And I want to solve for h in terms of k. So this is an implicit expression. If I can write h in terms of k explicitly, then this implicit function becomes an explicit function. Okay. So, but what is A of h comma k? It is precisely AXH plus AYK. So, A of h comma k equal to 0 if and only if AXH plus AYK equal to 0. Now solve for h. How do you solve? Take this to the right side. So AXH is equal to minus AYK. Therefore, what is h? It is minus of x whole inverse AYK, provided x is invertible. So the conclusion is I can solve this implicit function for h in terms of k provided x is invertible. And the solution is this: h is equal to minus of ax whole inverse AYK. And observe that this h is a linear function of k, because Ay is a matrix, Ax inverse is a matrix. Therefore, h is a linear function of k. And actually you will observe that this is precisely solving a linear system of equations. Which linear system? So this is A of h comma k equal to 0 here, 0 in Rn, 0 etc. 0 in Rn. So you have n plus m unknowns. These are the unknowns. How many equations you have? N equations you have. And you want to solve for h1 etc. hn in terms of k1 etc. kn. That is precisely you are doing. So this is essentially solving a system of linear equations. Okay. So we have now proved the linear version of the implicit function theorem completely. This is done. Now we will go to the general setup. So general version of implicit function theorem. So here there is a functional relationship between x and y, and you want to solve x in terms of y. That means x as a function of y. What is that functional relationship? It is f of x comma y is equal to 0. Okay, so the question is, under what conditions we can solve x in terms of y? So that functional relationship, that may not be a matrix or anything. So let us start with a arbitrary functional relationship between x and y, call it f, but that f is a C dash mapping, that means continuously differentiable mapping. Okay, so let f be a C dash mapping of an open set E contained in Rn plus m into Rn. In the linear version, we have the linear transformation from Rn plus m to Rn, but here it is not linear transformation, not necessarily linear transformation. It is defined on an open subset of Rn plus m into Rn, such that at some point a comma b, f of a b equal to 0. Okay, now look at the linear transformation a equal to f dash of ab. Remember, derivative is a linear transformation. So a is from where to where? This linear transformation is from Rn plus m into Rn. Okay, and as in the earlier case, assume x is invertible. Then, so this is the assumption. This is the assumption, and the conclusion is, then there exist open sets U contained in Rn plus m and W contained in Rm with a comma b in U and B belongs to W having the following property. To every y in W corresponds a unique x such that x comma y is in U and f of x comma y is equal to 0. So look at this sentence. To every y in W corresponds a unique x such that f of x comma y is equal to 0. That means x can be expressed as a function of y, satisfying the equation f of x comma y is equal to 0. But there are certain conditions. This that means given y there is a unique x. That y is not arbitrarily coming from Rm. Only in a neighborhood W of B you can take such y. Only in a neighborhood W of B you can take such y. So for each y in W, that means you are looking at a neighborhood of B. So in that neighborhood, that means essentially you are looking locally at B. Locally means in a neighborhood you are looking at, and in that neighborhood, for each point in that neighborhood, you can find a unique x such that f of x comma y is equal to 0. So x as a function of y we can write, but that is locally, not globally. Okay, and this x will depend upon this y. So if this x is defined to be g of y, so x in terms of y, explicitly you can solve, and if that explicit expression is x is equal to g of y, then the conclusion is that g is also a C dash mapping of w into Rn, and the thing is that here f of a comma b is equal to 0. And we want to solve here x in terms of y. So definitely we must have a equal to g of b. So this g is a C dash mapping of w into Rn, a equal to g of b, and f of what is x? It is g of y. F of g of y comma y is equal to 0 for all y in w, and more than that, the derivative of g can be computed at the point b. So that is given by this formula, minus of ax whole inverse into ay. So locally you can solve x in terms of y provided ax is invertible. That is the conclusion of implicit function theorem. So let me repeat. Locally you can solve x in terms of y provided x is invertible. നിങ്ങൾ ടെക്സ്റ്റ് വായിച്ച് നോക്കണം, യൂട്യൂബിൽ സെർച്ച് ചെയ്ത് കൂടുതൽ വീഡിയോസ് കാണണം. There are videos which explains the proof of implicit function theorem. I am asking you to refer to text or YouTube videos. Thank you.